Okay, welcome to today's lecture in deep learning and neural networks. After we've covered now different architectures in the last weeks and looked how you can combine different types of architectures to build your overall model. And we want to now go for the next step because now you have a nice model which has the capability of doing interesting things, but you have millions of parameters which you can't choose by hand. So we want to investigate how you can learn now these parameters. And as you all already know, this learning is called training, and that's what we will have a look at now the next weeks. We will start today with a basic training algorithm, especially how we formulate this then as an optimization problem. So you want to somehow optimize your parameters that these parameters represent very good your training data. And if your training data can be good predicted, of course, you hope that the same is true for your test data. And then we'll go to more and more advanced training algorithms. So next week is exercises, but the week after, we then, for example, look into how we can then deal with specific deep architectures. So, of course, this is not completely separable. It's not like, you can first define your architecture and then you research your training. But of course, both of them have to somehow fit to each other. So to start with this, what we're first looking is what do we need? We have a short look at the initialization, and then we'll look in generally how the training works. We're repeating that a bit. Just as a recap, we did discuss basic training in the first lecture, that we have to do forward, backward, pass, and so on. Of course, we also have considered the training when designing the architecture. It was always clear that we have to make a backpropagation because that is important. And then we'll mainly look today at two things. The first is what feedback signal do you get? So how do you measure how good your current prediction is? Of course, if you want to learn something, it's very essential that you can evaluate, that you can say how good is your current prediction. And therefore you will use different functions, and we'll especially look at binary cross entropy and cross entropy. And then if you now know how good you are, then it's a question how do you improve? And that we'll do with gradient descent. The idea is it's maybe better not to randomly choose any weights and then select which one is better, but you can use gradient descent, and that's where we need our backpropagation. So we check in which direction does the loss go down, and then we're trying to improve that. The basic gradient descent, I hope you're familiar with. We'll shortly recap, but then there's especially three things we want to have a look at. The one thing is how long should you train? When should you stop? That's the stopping criteria. Then there's a sampling size, which mainly decides on when should you update your weights. How do you make a good estimation? And most of that is then the last thing, the update rule, which will question how should you update your weights. Of course, there's somehow your basic idea that you're having your gradient and you do one step in that direction, but we'll see there you can do a bit more advanced to have a better learning experience. Good. Let's start with the introduction. So where are we? So we have now able to build these types of deep neural networks where we typically have multiple layers in there. So we have in purple here the input, in green the output layer, and then in between you can have any type of combination of layers that can be standard linear layers, but you also saw other things like attention and state space models and everything. You've also seen already at the end of last lecture, we had a look at the transformer architecture. So you see you can here, of course, combine also different things. We're not really having to care about that at the moment. We are just assuming it's we have a lot of layers, and as we define multiple layers, the input to one layer is then always the output of the previous layer, and so we can easily stack them onto each other. And each of these layers are defined by some function. Our hidden state, we are assuming that we typically assume two things. Either we have a vector that's like a fixed size representation, or we look now that's what we have mainly discussed in the architectures. Often it's not enough to just have a vector, so you want to have some structure of a vector. We mainly looked at sequences, but you also saw, like we also discussed already, images where you have a 2D structure of vectors. If you remember at the very beginning, we also looked briefly at like graphs, but in generally that doesn't matter here. We're just assuming we have some structure there, and that is the output. And then we have F, which is a transformation, so which does a transformation of hi minus 1, so the previous hidden state into the new one. The important thing, it has to be differentiable, so we have to calculate our derivation there. And for example, if it's an MLP, it could be something like activation function of some matrix AI times hi minus 1, and that will be then the result. This can also be an RNN or any of the other things. And yeah, so this is what we are currently having, what there is already. And now we have to the big question today is, how do we choose these AI or all our other parameters theta I? And how we are doing that, so at least in our current setup, we always assume that we're doing supervised learning. What does supervised learning mean? It means we know the correct answer. So in training, we always have as input our xi, our inputs, and then we're generating some output, and at the end, we know the yi, so what is the correct one? Can be in a classification task, it's the correct class. In sequence generation, it might be the correct sequence or anything like that. But it's important, we are always now having these pairs xi and yi, which tell us, okay, for this input, we are expecting to do this output. And in addition, and then we're looking, we have our loss function L, which can tell us how good is our output given this label. So it can somehow evaluate if you have the yi, how good is it compared to our OI. And we are now assuming, and we'll see, we only take very simple things. So of course, in a lot of real world scenarios, this is an overall very difficult problem. I mean, if you think about text generation, it's not easy to know whether this is a good sentence or bad sentence, or even if you know the reference, to know whether this now is right or wrong isn't that easy. You can formulate things differently and so on. We'll not care about this. This today will mainly just do a comparison, and it's mainly telling you if it's the right answer, it's good, or if it's giving much probability mass to the right answer, it's good, and if it's not, then anything. We're not talking about ambiguities, that there are some things might be very different classes, but they're still good. Or I mean, more simple thing in a classification, you normally only think the right classification is wrong, is right, and everything else is wrong. You're not considering if you give 5 stars and it's a 3-star, it's maybe better than it's a 1-star problem or something like that. We're just like mainly do a direct comparison here. And then we're of course doing that not for a single example, but we're typically like accumulating over all our examples. And then like we're trying to find a network where some of this loss is as low as possible. So you want to have that there's very, very few loss in there. However, let's do one, before we're going into the training, one very brief sidestep, and that is a question. Now I assume we can calculate our loss. So we can calculate how good the answer is. But how can we do that at the beginning? We haven't learned anything, so how can we make a prediction without training at the beginning? Yes?
Visualize the weights randomly.
Exactly. So that's maybe a bit surprising. You can just do random stuff. And we will later see it's really important to do it randomly. So just saying everything to 0 will not give a good training. So all the networks are at the beginning typically initialized randomly, and then you're starting from that and improving this random solution. It's also like it has random initialization has another example. So it's easy to build. If you want to have several models, it's very easy to build several models because you just do several random initializations. So you can take the same model, you do just different random initialization, you're optimizing it. And now you'll see a problem of our training is we're not finding the global best solution because it's like very difficult. There's like a lot of different solutions. You have a lot, like millions of parameters. You can't test all possible combinations. So you're ending up in a local minima. So if you do that several times, at least chances are high that you're not landing always in the same solution. So it's also your ability to take different types of things. Okay, so how does this training work like? So the overall idea is of the training is we want to find parameters theta which minimize our error on the training data. So there's now like several things which are important here. First of all, we're assuming a good network is a network where the loss on your training data is minimal. How do you do that? You do a prediction of your network with your input, you're comparing it to your output, then you have some function L which measures how good this prediction is, and then you're summing up overall possible inputs. So that is our overall goal. Somehow the best network would be the one where this loss is minimal. It doesn't need to be zero, and there's a lot of problems where it's contradicting, so you can't find a solution where you have always like zero, but in generally it is it is important to find one which is good. It also shows you already the training data seems to be very important because it somehow defines where you're interested in. Meaning, if you train two models on different training data, you'll also get different models because it might not be that the same parameters are optimal for both of them. And it also means like if you think about training data, it should be representative because you want, if the loss is there small, you want to have it also in other cases. So the question is, how can we now? So the nice thing is now we have defined our learning goal as just an optimization problem. So we can optimize that. The question is, how do we optimize it? So since random initialization worked quite nice for finding a good starting point, we could just do that just a lot of times. So we could like randomly guess a lot of possible points, always evaluate, and then select the one which is good. You would get a result, but this is typically very inefficient. If you think about, you have millions of parameters. If you just do always random guesses, they just all will be quite bad because normally what you assume is most of the area is really bad results and there's only like small fields where it's really good. So what is essential in deep learning and neural network is really this idea of gradient descent, that we're not just randomly checking things out, but all our network, the loss function, as well as our network is differentiable, and then we're not having to randomly guess, but we can go along the gradients and try to find a local optima. So this is here shown for like the 1D case, just imagine you only have one weight, and then you can you could draw the weight on the left axis and the error on the right axis. And you see when you're now at the green point, there is a gradient showing in this direction because the function goes up here. And so you go in the other direction, and then you're ending up here. So which it gives you now hopefully that goes faster in just putting randomly points here and trying them and then taking the minimum one. For one, that might even somehow work, but if you're going to know multidimensional, it doesn't work. Why don't you just select this value, which is somehow the best? Just look at the function and then select the one with the nearest one. Yes?
Evaluating the function is really expensive and you don't know if after the last mountain there is a value for it.
Okay, so you don't know the function. So the only thing you can do is you can evaluate it as you correctly said. So this function I draw out here, but we're not knowing it. What we only can do is can evaluate it on single points, like the green one here. So we only know the value here. And then we have to decide, do we take that or do we take another one? And then, as you exactly said, evaluating means to run your neural network for every example of your training point, if you're training data. So since you don't know the function, you have to like do all combination of that. That doesn't work. So what you're doing is you're evaluating here how good the function is at this point. And you're not only evaluating, you're also calculating the derivation. And then you can go in this direction and maybe evaluate here. That's now we'll look into. I mean, one question is how far do you go in your gradient? Do you just go till here? Do you go till here, here, here? Are you lucky go here, or do you go here, or even here? So that's now part of the algorithm. What is the right step size? But that is the overall idea. We don't know this function. We can only evaluate the function for one fixed point, our current weights. But we are a lot more efficient since we're not only evaluating there, but what we also do is we're calculating the derivation, and then we can go into the right direction. Then we can, of course, also do like in 2D, it looks a bit like that. So, of course, now it's getting more difficult to just imagine these are like isobaren, like they show like where the level is the same. And then you also have a gradient, and if they show now go deeper, then hopefully you'll end up here. And in reality, of course, it's not only 2D, but like 500 dimensions for one layer, and for all your layers, 2 million dimensions or something like that. And then you're always evaluating in one point, looking at which direction your function goes down and going in this direction. Okay, so let's have a look how the algorithm really works, at least on a high level. So the first thing we're doing is what we anyway did, and that way you also do an inference. You do what we call the forward pass. So you're calculating first your activate, or you have your input. Then you can, based on that, you can calculate the activation in the first layer. Based on that, you can calculate your activation in the next layer, and so on. So you can go step by step up, always calculating hi based on f of hi minus 1 and our parameters, and then you'll like step by step get all your activations here. That's the first part of the algorithm. The next part is now we can calculate a bit our loss here. So what we can do is we can check how good is now our current output. How good is the output given the prediction that we have? So we're calculating our equal sign here, the difference between the output and the label that we have, telling us how good the model is. But if you remember on the graph before, just knowing how good the model is not really helpful, because it doesn't tell us anything about how we can get better, how we can better make a bit better model. In order to do that, we're now doing the backpropagation. So based on that, we are backpropagating the error and calculating for each of our weights here, what is the contribution of this weight to our error? And thereby can calculate in which direction this weight should be changed. How are we doing that? So what we want to have is we want to have the derivation of the loss function of the output of the network compared to y given to our parameters. In the first step, what we have to calculate then is the derivation of the loss function with respect to the input of the loss function times the derivation of the output of the network with respect to the parameter. So first here, you do the derivation of the loss function and then of the network. That's a nice thing, and that's why backpropagation works so good, because you can like do up the splitting up of the full derivation into step-by-step processes with partial derivations. That allows us then to do all these steps. And that's what we're doing. That's why it's called backward pass, because somewhere on the network, what we're meaning is we're going down step by step with our derivation. So first, we're calculating the derivation of the loss function, and then we're doing that for each layer. So we're calculating again the derivation of the hidden state given its parameters, which is the derivation of the function given the parameters. And then you see here you have the derivation until this level times the derivation of the current hidden state there. And then you can also do it for the next layer, so of hi given ha minus 1. And you're just doing that really then step by step. So what we really have to do is like we have to calculate the partial derivation here at each time step in order to get then the overall derivation of all our functions. So the final thing of the backpropagation is that for each step here, for each layer, we have calculated for the parameters we use in this layer, we have calculated the derivation of these parameters with respect, the derivation of the loss function with respect to each of the parameters. So for the top layer, you've done that, for the second, and so until the first layer. For each layer, you have calculated what is the derivation of the loss function with respect to this parameter, so that you can then use this information to update each of the parameters. So even for this lowest layer here, you know, like in which direction you have to change it in order to change up there the overall thing. Of course, and that makes things a lot more difficult. It's only like you calculate the derivation with the information that all the other stays the same, and that will not do because it's too slow. So of course, if you now optimize everything in parallel, things might get complicated. But we are getting these information for each parameters, and thereby then can be more effective. What we then typically do is that we are not directly, or especially if you would now like to optimize the overall training data loss, you don't have to do that once, but you have to collect the ones over time. So if you give in one example you're using the current parameters in the forward pass, and then in the backward pass, you're storing the derivations. And that's now easy if you have now, because your loss function is the sum over all examples, which also means if the loss function is the sum over all examples, the final derivation is also the sum over all derivations. So what you then have to do in the next step is always add up here your derivations. So you store the derivations over number of samples that we want to do. Will be later part of the algorithm. But we're storing here always our derivations and then using that. If you remember, maybe it's a long time ago, but we talked about that a bit in distributed training, that you have to store. And when we talked about where to store information, you maybe remember that we needed to store like parameters in here to have the, and then there was a question where to store. So if you're doing your learning in the forward path, you're using your weights, and then on the backward path, you always have to store your current derivation so that you can sum them up for all the examples you want to do. And then is your final step. So what you then want to do is like you update your parameters now with the loss with respect to these parameters. And yeah, so this is the overall algorithm that you have to do. So always you have to do these steps, meaning we start with a forward pass, then we're calculating the loss, then we're doing the backpropagation, then we're summing up our gradients, then we apply our update rule, and then we have new weights, and then we can start over again. So then we can again do the forward pass from some other data, calculate the loss, and hopefully do something like that. So if we're one step, we maybe start up there at the green point, then we're looking at a lot of examples and hopefully have the right direction of our loss. Going to that point, then do it again, and slowly we hopefully end up here. Doesn't mean that this needs to be like a global optimum. That's some of the problem. How would the error function needs to look like if we're always ending up in a global optimum? Ready? Yes, it's true. There's more quadratic function are one of the functions which have a special property so that you're ending up.
convex.
Yes, exactly. So it has to be a convex function so that when you're going down, you're landing it. This is not true for your parameter space of a neural network. So it's not convex at all. It's like very, very crazy. And that's why we're seeing that you need to do like a lot of tricks and maybe doing restarts. However, this is of course it's still a very good way of going into the right direction. In order, to make your system successfully learn things, what we now hopefully saw, there's two important things we have to, or we will cover in more detail. The one question is the loss function. So how do you tell how good your current estimator are? This is something very essential and important for training your network. So how can you, and that depends, for example, on what type of network we're using. We'll look here at very simple things, but at least that should be clear. It's also like correlated therefore strongly with what you want to predict. The other important thing which we will cover is how do you want to update your network? So this is of course an easy way of doing it, but we'll see if you just do normal gradient descent, it might not be the good thing. So there's already here one Greek letter. What do you know for what this stands for? Yes, exactly. So that's mainly like how big your steps are. So what you only have from your gradient is the direction of the arrow. Now, the question is how far should you go in that direction? If you're going far, the nice thing is you're learning faster, so you're going faster, hopefully in the right direction. But if you're doing it too fast, maybe you're ending up here and then you're like going up and down. So that is like the first trick how to best select your learning rate. And then we'll see maybe it's better not to have like somehow a fixed schedule to always go like in a fixed length in the right direction, but look how you have done before in order maybe also in different dimensions go into different speeds to select then the best ways of doing this. Okay. Yes, and with this motivation, let's have a look now at the two main things. On the one hand, the feedback signal, so the loss function we want to do, and then we'll have a look at the gradient descent and see how we're doing that. Any idea what could be maybe the most easy way of measuring the error in a neural network?
Take the mean error.
Right. And that's a very good thing, to be honest. And for a lot of tasks, it's really what we do. So what do we have? First, maybe that's good to think about it. What we have on the one thing is our output OI, and OI is typically like a vector which we want to compare. And then we have YE, which is a ground truth, and it's also a vector. If you want to do a comparison between vectors and select how good these two are, is you're taking the mean square error and just measuring how this is done. This is, for example, typically done if you do some type of regression, you're trying to predict something, then this is a very good one. What we now want to do a bit more is there's a lot of neural networks you now already heard about, which are about classification. So either two-class classification or multi-class classification, and or better say, about categorical values. So even like we saw that already a bit, that if you're doing, for example, text generation, it's also some type of classification task because you're classifying what is the next word. And of course, you can also use this one in a classification thing, but it has been shown that in classification tasks, some other type of model seems to work a bit better. Okay, so and therefore we'll also look into how we represent the output. So the first thing is the binary cross entropy task. Where is a binary cross entropy typically used? Just imagine you have a binary value at your output, and your network should somehow optimize the probability of this label given X. How you typically model that, if you have a binary class, is you only can have one single output neuron, and then you're doing like the probability of ye given x is the output. So if ye is 1 and if ye should be 0, the label, then you can get the probability of 0 as being 1 minus only. That's a nice thing. If you have binary, you only need one probability because then you can directly get the other probability because they have to sum up to 1. So the other value is 1 minus this one. So you have this binary problem, and then you have as output the probability that the label is 1. And to get the probability that the label is 0, you just do 1 minus the output probability in there. If you want to learn these type of things, it is good to, or like one a successful loss function is that we're trying to maximize the logarithmic of the probability of the right label. So here you're going again over all your training examples, and then you're trying to maximize the probability of the label given x, the logarithm therefore, and since we want to have a loss function, so it should be negative, so you want to minimize, you're minimizing the neg log prob of that. So this is just like, yeah, so we're saying we're not trying to optimize, I mean, we're trying mainly the loss function, which measures the similarity, is now the logarithmic probability of that. If the probability is high, that's good. If the probability is low, this is bad. You can formulate that now a bit different. So what does it mean of the correct label? So if the label is 1, you want to maximize the logarithm of the output. If the label is 0, so 1 minus this one has a value, then it should be ln 1 minus O. So, and this is like your formula of the binary cross entropy. So in the binary case, you can have two cases. The one thing is your label is 0. In this case, this term is 0. And this term is 1 times the logarithm of 1 minus the output. If you look up there, that's exactly the probability then of this label. The other case is your label is 1. If your label is 1, then this is the probability of the thing. So 1 times the probability, so the probability of the logarithmic probability. And this one is then 0 because 1 minus 1 is 0. So you're exactly doing this one. So if you're using this loss function, that's exactly what you're doing. So you can do an easy way of doing the binary binary classes. So we can train a binary classification problem by that. And if you have that, a typical thing you want to do is binary cross entropy. Just optimize that. Now, that's wrong. No, but there's often the case that you don't have a binary classification problem, but you have maybe more classes. And then you can easily now extend that. And that is how you train typically a general cross entropy loss. And so how does that work now? So in this case, we already had a look at it. If we have multi-class classification, input or output, we're typically representing our output in one hot encoded. So if you remember, we have that for input and output. If you remember the weather, if you have cloudy, sunny, or rainy, you would have 3 classes. So you have a vector of 3, and each one is like 1, and all the others are 0. Now the question is, how do you now do the output? If you have not one output neuron, but several, and you somehow want to have a probability distribution over all your possible outputs. So if you have 3 classes, in the end, you want to have somehow all the 3 probabilities. The nice thing in the 2-class case, it was possible to do that with 1 neuron, because the other probability wasn't always clear. Now, of course, things are a bit different, and that's why you typically have here 1 neuron also for each possible class. How you're doing it is, in a multi-class problem, you're having each neuron should represent the probability. So this is a probability that it's class 1, class 2, class 3, and class 4. Now we somehow, of course, have to make sure that this is somehow still a probability distribution. We want to work with probabilities at the end, and that can be achieved with a activation function. Does anybody know how we achieve that this is a probability distribution?
Max,
And
softmax function.
what is a softmax function?
It sums all the probability or the logics to one. So the summation of all the probabilities are one.
Exactly. So there's even two things they have to make sure. One, the sum should be 1. The other thing, they should all be positive. So it shouldn't be negative values because it's probabilities. And you achieve that if you take your activation, which was a blue one, here, and then you to e to the power of the activation, then this one is positive. And then you normalize that by dividing to the sum of all the e to the power of activations. And then you hopefully get in red this probability distribution. And if you look at this one, since this is positive e to the power of something, this value is always positive. And if you sum up now for all the classes these values, you have the sum of k a to the power of I divided by the sum of k of a to the power of ak. And then hopefully you see that your numerator and denominator is exactly the same. So that will always be 1. So with this one, you're somehow ensuring that you have at the end a probability distribution. And yeah, this function is called then the softmax function, which you typically do on your top layer. So in your top layer, you always have the same number of hidden or like of units as you have classes. So 1 for each class, and then you use the softmax activation function, which will then give you the probability distribution. If you have the probability distribution, now it is easy again to do to calculate the not binary cross entropy, but cross entropy. Sorry about that. So this is a cross entropy. So what you're doing is you're summing over all classes. You're doing y(e) of k, so the value of the class. So in this one, only one element is 1 and all the others is 0, because we have again the one-hot encoding of your labels. So on the label side, we have that exactly one class. We're saying it belongs to that class and all the others not. So here is only one value, 1. And then we're trying to maximize the probability of that. So if you look at this again, so you're having your labels where one element is 1. And then what you're doing here is you're comparing that and looking, and what you want to do is you want to maximize this probability. That is your aim, or like minimize that and not make look. So you're trying to maximize here the probability that this element is right. That sounds now a bit surprising because that would mean you're trying to optimize this one, the probability, but you're not giving any feedback to all the other classes. Seems to be not super good. Are you really doing that, or? Yes?
Because of the softmax, if value is higher than the other, it automatically gets scaled down.
Exactly. So if you try to increase this value, you can increase this value by then you're automatically forcing the other values to somehow go down. So because this value is not only calculated by the edges coming in here, so the activation function, there's like normalized overall, which also means like after the softmax layer, you're giving feedback to all the other layers too. So you're not only giving feedback to the correct one, but through the softmax normalization, you also give feedback to all the others. So really the whole network is trained and not only like the one. While it might be still, or it's still important to remember, so we're comparing two quite different vectors. So the one vector is like very sparse. We only have 1, 1, and everything else is 0. While here we have a probability distribution where each value is typically between 0 and, or is always between 0 and 1, but typically it's not sparse, but it's really a probability distribution. Good. Any more questions on? Yes.
Why is cross-entropy preferred over KL divergence?
Oh, over KL divergence. I think it's more stable in training, and that has been shown. That would be the one I would guess now. Oh, and I mean for KL, I mean this is the probability. This is not really a probability distribution. I mean it is a probability distribution, but a very different one. And maybe you even don't want to have. I mean, what you want is that there's a lot of probability mass here, but in a lot of tasks, it's even interesting that several are good because if you think about some generation tests, it might be that there's like sometimes the one is good and sometimes the other good, and both could be good, but you're only getting feedback. So you're in text, you're not always seeing that all these are the right examples. You're only seeing one good example. Yes.
How do you make sure that the probabilities actually correspond to the probabilities that you want? For example, if you specify something, and in 50% of cases, to say there's a 130% probability of this being the case, and in the other 50%, it will probability if we don't, and your probability on average will not really reflect your actual want probability.
I mean, that is so what you sometimes take is you take this output probability as a confidence estimation. So how sure are you that it's doing, with the assumption that if it's exactly doing, if it's very sure, then that should be a good answer. And it's a good first approximation, but it's not perfect. The problem is we don't know really the probability, we don't know which probability distribution we want to have. We only typically have a single example telling us this is right, but we don't know, and we're somehow assuming this formula. All other examples are wrong. So you only try to increase the probability, and like the other ones, you're not really forcing. That's a big disadvantage. However, in a lot of examples, this is just what we have. We'll come to that. So that's, for example, one thing where successfully what people call knowledge distillation is of advantage, because there you take maybe a bigger model which can estimate a good probability distribution here and use that as training signal, because then you maybe have a much stronger training signal. It doesn't only tell you, oh, this is wrong and everything else is this is right and everything else is wrong, but it tells you, oh, this is how the distribution should look like. But we'll come to that later I mean, the problem is this is more, okay, this is all we have, so we have to deal with that, and that's good. So this is about the feedback signal. Now we want to look again at how we are doing the gradient descent algorithm. But before we are doing that, any questions? Good. So how does that look like? So here we have the basic algorithm, which will like repeat and now make more and more complex. But let's start with a very, very easy thing. So what we're starting with is we have our fixed learning rate. Remember, we had that, so we're always going a fixed stepwise. And we have our initial parameters, so theta 0. So there's our initial guess parameters at iteration 0. When preparing it, I have to admit it's a bit confusing. Maybe from now on, we're talking about the different iterations. So theta e is now the parameter iteration e, and no longer in layer e. I hope you can get this jump. So here we are no longer considering the different layers. It's just one network, and we're not considering different layers. So here in e is like the iteration we're taking. And what we're then doing is we're doing for some time, we're going over all our examples. And then like for the iteration, we're going over all examples. Then we have to compute the gradient. So this was mainly the whole algorithm we had before. So you do the forward pass and you do the backward pass in here. So this looks like a short line, but this is a lot of computation. Then you sum up all of them. That's we had in the picture before. So every time you do your backward pass, you add up your gradients, and then you apply your update rule. So your new parameters are the old one minus learning rate times the derivation, and that all the things you're doing repeatedly and repeatedly again. Then since you're going into the direction of your gradient, you're hopefully going down and will end up in some local minima. So this is the overall idea, but there's now several points where there's hyperparameters or design decisions, and these ones we want to look into now the rest of today's lecture. So the first thing is we're just saying here, while stopping criteria not met too. So as long as we're interested, we're continuing to learn. And this is the first important decision. So what is our stopping criteria? So how long do we want to do that? When are we think we're really done, we're good, and we don't have to continue anymore. And that is somehow very important in the learning, that you find the right time. And we'll look at that, so that you find the right time when you stop with your training. The next question is, how do you calculate your update? So which gradients do you sum up in order to calculate your gradients? If you're really going about gradient descent, what you really have to do is really go over all your training data, calculate the gradient, then you know, in order to be better on the whole training data size, I have to go into this direction. And for small, fun neural networks, that is possible. But if you're not trying to think about your training a large language model on the whole internet, that might not be the best way. What it means is you would have to go through all your text data. Then you know, okay, I have to go a bit in this direction. You train for 1 week or longer, and then you know, okay, in which direction you go. You do one step, and then you have to train another week. So that will not be a good thing. So this is somehow called, again, the sample. So the sample on which we calculate our update. And of course, to be correct, you have to do it in order. But maybe if you have a big enough sample size, it somehow tells you already a good estimate in which direction you want to go, and then you go in this direction. So that is the next thing we'll talk about, what is like somehow a good sample size. And then there is the final thing, which we should have a look into more detail, and that is how we are doing these updates. Of course, this is completely correct, and that could reach us out to the A. But now we have to consider one thing: is with this update rule I said shortly before, is we're only reaching the global minima, and we have a convex function, and that is not true in our case. So we are always in this problem that we wind up in really bad local minima. So there we have to somehow do two things to consider. On the one hand, we don't want to end up in, like, maybe there's this small local minima, which is really bad, but just the nearest. So if we're once ending up there and then can't go out again, that would be really bad. On the other hand, we have to make some type of progress. So if we're like doing very, very minimal changes, it's also like we're getting nowhere. And on the other hand, if we do two big jumps, we are just randomly jumping around. And then we are mainly not doing any gradient descent anymore, because we're just doing random selects in there. So we have to be a bit like, there's a lot of research on how to do that, and we want to look a bit into that, and then end up, which is called the Adam optimizer, which is somehow the default thing you will probably use nowadays. So if you're training a network and just using one, that is the thing you're using. So let's start with the stopping criteria. So even if you have like the perfect convex function, so a very nice function, this is what will happen. So you start your time with a very high training error, and then you're doing your steps. Since you're doing a gradient descent, your error should go down, and then finally you have here the minimal training error. At least that's one. Even if you're doing like in the local minima, it's the minimal one you're seeing. So this would mean, okay, it's always better to train as long as possible. Just train as long as you can, and then you'll have your minimal training error in here. Does anybody know of a problem that could occur?
Maybe we'll overfit on the training data. So when we use the model on the test data, it will give bad results.
Yes, exactly. So what typically is happening in neural networks is they're heavily over parameterized. So it's just successful that you use a lot of more parameters than you will need. What would mean that if you're just training on your training data, maybe at some point you're just learning all the examples by heart, but that doesn't generalize anymore. So you're not really good at other. You're just learning by heart that this one is good and nothing else. And this, of course, is not what you really want. So that's hopefully, and we did that at the first, what you know in machine learning, it's important. Your error on the training data is a first nice indication. That's what you optimize. But what really is interested is how good are you on data that you haven't seen? Because of course, we had the assumption our loss function when we in the optimization function that we minimize the error, but then we might minimize some specific things of the training data that we didn't know of, and that are just there also, and we're only getting good at predicting this one, and that is somehow not helpful at all. So what might happen is something like that. So in red, we have now the test data, and the error normally, like at the beginning, you're really learning something, things go down. But then at some point, what you're learning is no longer really like general information, but you're learning some specific things that only happens in your training data, which means you're over concentrating on that. And then typically you see that your test error goes up again. And that, of course, is not helpful at all. That's not what we want to do. And therefore, the stopping criteria is important. So what we really would like to do is like somehow stop here. Because if you stop here, that's like where on the test data, we are good. And it doesn't really help us if we're then getting better on the training data. It would be good to just stop there and stop further training. So any idea how we can do that? Guess most of you have done it already. Yes?
That we evaluate the problem.
Yes, exactly. So we can't use, of course, our test data. You should not look at your test data. Well, what you can do is you can observe another validation data and that you typically have. So you have this additional validation data, and maybe they are not perfectly the same. So it might be that a bit earlier or a bit later, your test error stops. But what you can now monitor is like, when does your validation error go up again? And that might be a good starting point. You see, it's not perfect, but normally you can't be perfect in everything, but it should be a good point to stop. So what you're doing typically is between the training, from time to time, you're evaluating also in the validation set. And if here the error goes up again, you know, oh, it's better to stop now. Yes?
Would you, in this case, use a K4 as validation thing method? Way worse result.
And I mean, you could do that. I mean, that normally do k-fold presentation if you have limited data, that you typically do. The problem is that, I mean, either if you take it from a training data, you have in the end k models. So which ones do you use in the end? Because you want to have one. And you, of course, have to run 10 training times, or if k is 10. But it's if you have that, that's a good way of doing that. If you have more data, you can, I mean, nowadays often you have a lot of training data, so you can just take a random subset of your training data. But k-fold validation is a good approach there to just say make things a bit more complicated. So if you really need all of your data, that's what you're doing. We're now considering a bit on the more simple task where you have a validation set, and then you're just stopping when you do your validation. So you monitor all the time your additional error, and then your stopping criteria is once, like to take the value which has minimal value on the validation set. So if you stop earlier, you do what we call underfitting. So you could just get better if you learn more and more. And for the validation data, if you go further, you do overfitting, and then you can't. You're not really optimal anymore on your unseen data. So what it mainly mean is like from time to time, because you might not do that at each step because it like takes time again to evaluate all your validation data. But at different points, you evaluate your current model on the validation data, and then once it goes up again, then you're mainly saving the model with the lowest error on the validation data, and then you're taking the model which has the lowest error on the validation data as your final model, and that's mainly then your stopping criteria. So of course, I mean, you only know that this one is the final one somehow here or here, and so you have to somehow store that this one was the best. Also, often it's not as nice. So if you see real curves, they more look like this a bit. So that's why once in most early stopping, you're not saying, oh, once it's going up, I'm stopped. It might go down again. So you're saying if it hasn't improved for X evaluations, then it's a good point to stop. And then you take the model with the lowest score. Because, I mean, this is a bit nicely drawn. Reality, the loss looks more like this, and then you might have some up and downs in between. But yeah, so that seems to be a very easy way of evaluating that. Since we can't do it on the test data, we just create us our other test data, which should of course have a bit like a similar relation. The good thing is then we can't learn because this validation data is only there for testing. It is not used for training. It doesn't give us any training signal. So we can't easily learn like the characteristics of that data. And therefore, we're only using it to decide then when is a good point to stop and use that. Good. Do you have any more questions on this early stopping or the samples, the stopping criteria? Good. Then we can go for the second point, where the second point was now the sample size. So just to remember, where was that? So now we have here the stopping criteria, where the stopping criteria we now saw is a bit of extra calculation because we have to evaluate the model on a different data set. But now the question is, which gradients do we sum up? That's mainly the question. So how do we calculate the gradients? Where, like we saw, the original loss function is taking the average of the whole training data. So the question is, what is really the best to do there to do like summing up all our gradients? And there is different ways of doing that, and therefore also, yeah. So the first thing you can do is you can do what is called batch gradient descent, meaning that you're doing one update after each epoch. So you're running one iteration over all your training data, and then you would do your update. So it's the correct thing according to our loss function, because then you're really minimizing, only in this case, you're minimizing the overall loss of your old training data. But it is very slow. So especially like if you get larger and larger data, it also means your training gets slower and slower and slower, because the more data you have, the longer it takes to do one iteration. So you have a very slow conversion. And that is why, at least in large models at the moment, you wouldn't do that, because it takes really, really long time to go over all training data. So then, of course, you can do the other thing, which means, okay, we just don't do the average. We're just like do stochastic gradient descent, meaning every time we're just taking randomly one sample, we're taking this sample and then doing the updates. So we're not like summing up the updates. We're always taking one sample, doing the update, and then going on. So if we look at our algorithm, so the change would be instead of like going here over all examples, computing the gradient and summing up, now it looks like that we're sampling one example, we're calculating the gradient, and then we're applying the gradient. Does anybody have an idea what could be challenging in this condition? Any idea what? Yeah. What happened there? Just
There might be noise in one single data point.
yes, exactly. So if you now have one gradient calculated by one data point, it might go in this direction. Then you have another data point which just gives you a different learning, and it's going in the complete other direction, which means you're not really have a strong learning signal, but you're going like crazily across, and then your training may not be really stable. So something, I try to visualize it a bit, something like this happened. You start here, then you're going in this direction, then in this, and then in this, and this, and this. So you're mainly going crisscross on your data, and then, of course, you're also not having a good learn. But if you just trust one, I mean, just imagine you could be that you just have two examples, which, when if you have a class, which or is the same input, which sometimes can have the one class and sometimes the other class. So you have two labels for that. Then your model will always go back and forth because the one says go to this class, the other says go to that class. So you're somehow having not a strong signal, and that will not be like a good, a good learn. However, now we have seen two extremes. So once you do your update only after each epoch, once you do your update after each example, I guess now it's not a big surprise that you might be good to do something in between. And that's what people refer to as a mini batch gradient descent, where the idea is we're not taking one, we're not taking all, we're just taking a fixed number of examples. So we're taking an example. So now, of course, everything comes with a bit of a disadvantage. The disadvantage now is just another new hyperparameter, which we have to somehow care about. So there's a new hyperparameter which we have to use. But then what we're doing is we're calculating our gradients for n examples. We are like then doing the average of the n, and then doing this as update. Meaning if there's two examples which just inform us exactly the opposite, maybe these two are cancelled out, we're ignoring them, and we're just using the signal from the other more reliable examples. But we're not going always back and forth, but we're like having a stronger signal. So you're not like every time somebody tells you you're exactly doing that, you're first asking several persons, then looking what is their average meaning, and then saying, oh, this might be a good direction. And there I go any further to it. So how does that work now? Again, so we have to change a bit. So we're getting a batch. So we have somehow the sampling in here again. So we have somehow to decide which samples we're looking into. Then we're going over these samples. There we do again the calculate the gradients and sum them up. So we're summing up them. And at the end, we apply our update with just the average of all of them. So we have now a bit of both. On the one hand, we're not always taking everything. We're just taking a batch here. And then we're going over this batch and applying the thing. So now, of course, we have the new hyperparameter, which also means good thing is you have something where you can like improve on. Also, bad thing you have another parameter you can mess up with. So what should be considered in there? So there's first of thing, what is a good batch size? So on the one hand, if it's too big, we have the same problem as before. We have slow learning because it takes very long. If it's too small, you have the noisy gradient. So you have to somehow find a bit of a medium thing, which makes it even more challenging. It's not like the same for everything. So it really also depends on what type of network you have. So for example, when like self-attention and transformer came out, it was like shown that you need like a lot larger batch sizes there. So you couldn't do as many updates as, for example, before from earlier. So you really have to like adjust it a bit. However, there's nowadays typically good estimates on how to do it. things are getting even more complicated is that what does now a batch size of n mean? If you just have a classification task, it's maybe quite straightforward. In one example, you get one feedback signal, and that is good. Now, think about the loss function in a sequence. So if you have a sequence, you're not, if you remember, if you have the transformer or so, you're not getting only a feedback at the end. You're getting at each position a feedback. So you're getting different number of signals there. So how should you call now an input like a long sentence as one, or should you count it as n because it has n words? Also, like in order to comparison, if you do now the average, what you do here, you're averaging your loss, therefore it's all the n. So the one thing is you're considering the loss you get for a long sequence the same length as the loss for the short sequence, although there is a lot more loss calculated and maybe you get more feedback signal. Or should you take this n as a sequence length, then of course now it's like no longer, if you have say like a n of 500, it can be that it's like 2 sentences with 250, or it can be 50 sentences with length 10. So that's again, of course, a bit of a decision that you have to take. I think today it's mainly that you take it by sample, so like by words, but again, that you have to decide. And then finally, there is the sampling strategy where you can also do both. If you sample enough, it hopefully shouldn't matter anymore, but you can do both. So again, just sampling without displacement, so just always randomly sample, or you say, oh, I want to make sure that like all of my examples are seen equally often, which means you would do something like a sample without replacement, no, with replacement, without replacement, yeah. So that you're like, each element is counted as, so if you have selected 1 and 2 already, then you can't do that. Next time you have to take other ones. Again, that's a bit of decision on your sample. Now you should be not only a bit confused about this, but there should be one term which a bit like might have confused you already, because we used this term before already a bit different. Anybody remember a term that I just used? It used before differently. I have to admit it some lectures ago. Anybody remembers? We had it here, I think. We talked about the batch. Anybody remember where this term of batch size and batch already occurred? Yes?
GPU lecture or something?
Yes, exactly. So that's maybe a bit confusing and it should be clear. So there's typically 2 types of batch sizes, which are not exactly the same, but they are related and you should know. So the one thing is now we have the optimization. There we're talking about a batch size optimization, and that is the number of examples you're doing before you're doing an update. And so we saw that you define your batch size and then you're doing only updates after that. And there we mainly have this trade-off between the stability on the one end. So you want to have enough examples that your gradient estimation is stable. And on the other hand, convergence, if you're doing too many, it just takes too long and you'll forever. Then there is another thing, and that's the GPU batch size, which means that is the number of examples that you parallel calculate. So we saw that for GPUs, it's very efficient to not give one example and wait for the results, but you typically give n examples and parallel calculate the output and then get the result. And there was more the trade-off between, on the one hand, speed. The larger your batch size is, the larger normally also your speed is, but you have some restrictions on the memory. And first, of course, these are a bit independent. You don't have to do them the same. However, there is a relation between that. So your optimization batch size has to be larger than your GPU batch size. Why is that the case? Yes.
Resources otherwise, because we don't use all the. You can calculate it well.
Yes, if you're, it depends. So what happens if your GPU batch size is bigger? So if you update, like you run 100 examples in parallel, but you want to update after 50. It's not really possible. So I mean, you can use it in waste because you throw away the last 50, okay, but normally, I mean, you can't update within one calculation here. So you can only update after you have done the calculation. And that's why your GPU batch size has to be smaller. Typically, and that's your point, that's why you do like a multiplicative of that. So for example, I mean, you also waste if you now do like your GPU batch size is 100 and you say, oh, I have to optimize after 150. That's also not optimal because then you first in your first batch do 100 examples and then you only do 50, so you waste half of it. So typically what you want to have something like n times the one. So if you have maybe a GPU batch size of 32, then you maybe do optimizations always 128 examples. Then you do 4 batches. Then you have the 100 examples, and then you can do that. There's also like different things on how you select your batch thing. So for your batch O, what you would like to have is, I mean, what is the aim of the batch? So it should give you a rough, good estimate of in which direction this one goes, which means this should be somehow random to have a good example. Just imagine if you would do now sequences, you would only have short examples in your batch. Maybe short examples are somehow classified differently. So if you then would only learn on short examples, your direction might be very different than for the long. So you want to have a good overall distribution there, not everything in one direction. For the G, it's different. There you want to have all examples look a bit like the same because then it's easier to train. If you think about it again, long and short sequences, in the GPU, they all have to look the same. So you have to have the padding, make them all the lengths with zeros, which you ignore. And since you ignore that, of course, it would be nice if all of them have the same lengths so that you do that. So what you, for example, successfully often do is you sort your data, then you're sampling randomly a batch G inside this, making sure that inside the GPU batch, they all have a very similar length so that you don't waste a lot of calculation on different lengths inputs. Good. Any other questions before we are coming now to the last one? Yes. This is a good point. This is so right. My autocorrection did, I guess, B is big at the beginning. Oh, it's okay. So it's the same B, and I have only one B O and one B T. Thanks. So with this one, we're coming now to the last part, and now we have our update. We told what we should update for our derivation. So how do we do a good update? And the first hyperparameter there is the learning rate pattern. So we have to somehow select a good learning rate. And then there is like different ways of how we can do them, especially also like dynamically adjust them. So the first one is you can have a typical learning rate schedule where you say, oh, the learning rate should decay until some fixed iteration, and then it will stay stable. Saying at the beginning you have a very bad overall model, so you want to fast go into some good area, and then you don't want to go too far anymore. So at the beginning, so your N0 is the lower one, is the bigger one. So at the beginning you're there, and later you only have like a very small learning rate going in there. So you're trying to somehow have two different learning rates, one which is decaying first, the N0, which is big, and then later you have a smaller one, and always only one of them is, or like the other one doesn't disturb, and later only the other one is working. But that is, of course, maybe not everything. There's a lot of motivations, and now you can look how the derivation work over time to motivate you to maybe speed up the process. I mean, this is the overall process. You want to not always learn the same, but now you can also like dynamically do it and decide, oh, currently it's going in a good direction, so I can go faster. And if you have signals which always go in different direction, maybe you should slow down and like look more in detail. And that is called what is the gradient. And there, the idea is to introduce this velocity and have a look on how the gradients behave over time. And the main idea is if I always go into the same direction, that might be a good direction. So I can go faster in this direction. If I always switch my directions, maybe it's good to like not go too fast because there's anyway not clear where to go. So how can I do that? I have my velocity, which is the exponential decay of the gradient. So what you mainly do is you take an alpha value of your previous velocity and then subtract your new direction, and then you're always updating with it. So what you're doing here is you have your gradient, you have your velocity, and you add them up, and that's then the direction which you're really going to. So you go then in the direction of where you really want to go, and not always in different directions. So here again, as an example, so if your alpha is 0.9, you're always going in the same direction, then you're seeing how you speed up here. So in the beginning, you're having your learning rate. The next time you have alpha, so the previous one is this one, so you put in the previous one here. So now you're going 1.9 times this direction. And the next time you're going 2.71 times this direction, and the next time 3.44. So you're always going faster and faster in this direction if the gradients are the same. Of course, this is only true if the gradient's the same. So gradients go in different directions, things are not happening the same. So you have to, but that is exactly what you want. You want that if the direction is good, you're going faster in this direction. If it's like always switching, it makes sense to like slow down and look that. And that is somehow, yeah, the momentum term which tries to address this. There is now a variation of that. It's quite old idea from '83, where the idea is maybe instead of like here, we are calculating our gradient, then going also in this direction with our with the velocity. Instead, we are first going into the velocity because we know anyway this is a good direction to go. Then we're calculating our gradient there, and that is our actual step. So the order is a bit different. So what you're really doing here is you're not calculating your neural network at your current parameter size, but at your parameters plus the velocity, and doing that step already before and calculating the gradients there. So yeah, it's a minor change where you're not taking. You see here, nice. The thing is mainly the same. The only difference is where you evaluate your network. Do you evaluate it at your current position, or do you evaluate at the position where you already have done your step with your velocity in this direction? And then you get, yeah. So what you're now doing is so you're doing your calculating your gradient before, but now you're first computing your velocity here with the update, and then you're applying your update at the last step. So you're now adding not only the derivation of it here, but you're also adding that you're going in this direction, so you're adding this part to it too. Any questions about that? Good. What we have done until now is I mean, maybe there was a bit the idea from the 1D case, but to be honest, we have a very high dimensional case. And there it might be good not to use the same learning rate in all the directions. It may be that in some direction it's very clear in which direction you should go, and in other directions, no. So you somehow assume to have something like the red one up normally, that it's good to go equally in the same direction. But in reality, you might have something like that, which is more stretch on the x-axis than the y-axis, which means maybe on the x-axis, on this parameter, you speed up more, while you shouldn't do the same speed up like on this direction. So therefore, there is this downscaling by the square root of the historical values. So if the derivation is anyway large, we are going very fast there, then we maybe shouldn't speed up too much. So you're like going down there with the learning rate faster, and where you have only very small updates, if you do as fast, like remove them, then you're not doing anything there. So maybe there you have to speed up things a bit more, that you do any type of progress in there. And that is done with the so-called Adagrad algorithm. So now you see what you're doing is you have also R, which is just like taking the square of your thing, of your gradient. So this is the gradient and this is the gradient. So what you're mainly doing is you're saying like, yeah, if the gradient is very large, maybe we shouldn't speed up as much and slow down a bit. So this is a summed over here again, summed over time. So you sum over time how many updates you have done already. And if that's very high, you're like dividing here through the length. So you're normalizing it a bit, that not like in one direction you're going super fast and the others you're not going that fast anymore of your update. And then you're again applying this velocity to your original thing. So the idea is that that you're now doing that, but now we only have done this changes in there again. So we didn't take the velocity in there anymore, and this is now done in the no, sorry, that was wrong. I did the one more. So here now you're taking all the averages all the time, the same one. So one might be better is you're doing like an average, like an exponential decay. So in this one before, you're taking the average over all examples, and maybe you want to more take the last ones more into account. And that's what you're doing now in RS prompt. So here the first one is as important because it's just the sum over all the examples. So what you're doing here is now you're doing the weighted sum. So your previous example gets weighted down, and then you're adding them up. So since the previous one are always multiplied, the longer over was better. So the first one has I times already better in there. So it's getting lower and lower influence, and you're mainly focusing on your last example. So you have this exponential decay that for taking into account how much you should go into this direction, you're more focusing on the last updates. And if you at the beginning had very large changes there, it doesn't matter anymore. So that is then the add up from Adagrad to RS prompt. So we are still like normalizing by the length, but we are no longer taking all the same, but we are like don't consider the very early examples anymore as fast. Now we have lost one thing again. What did we just ignore starting from Adagrad? We had some idea in between. Did you remember? In this formula, there's one idea we didn't have anymore.
The learning rate decay?
The momentum, yes. So the momentum is no longer there, so it might make sense to have both of them, and that's then combined here. So we have for normalizing the square, but then we are not updating by only the current one, but by the weighted average over all of them. So we have the velocity in there again. So on the one hand, for in which directions we are going, we are not taking only the current derivation, but also the previous ones. How strong we consider them, we're taking the square roots in here. And then we're combining both here and to get the final one. Now we are nearly there. So there's only a very small change now to what is called the Adam algorithm. So what you now do is what is called the unbiased. And that's only important at the beginning. So at the beginning, you have here the M0 and R0, which mainly is like has to be 0 as you have to initialize that at some point. And maybe normally you initialize that with 0, which of course is not true, which mainly means at the beginning, you're not considering really your derivation, but you're taking only 1 minus beta 1 of the derivation. So you're lowering the derivation because you can't do like an exponential decay of that because you have now past values that you consider. And that's why you normalize them already and undo that by normalizing that to the power of I here. So how many iterations you have. So the more often you have done that, there's less normalization happen, and it's mainly then this will go, since this is smaller than 0, this will go to 0. This is smaller than 1, so it will go to 0. So you mainly, and if you're having many, many examples, these two values will be the same. But at the beginning, you're undoing that you're also considering the past. So it's mainly the thing. I mean, here we learned that we normalized over the past. So we're also considering the past. The problem is at the beginning, you don't really have a past. So your past is just zeros, which puts too much effort into zeros. So you're doing the unbiasing, and then you are more successful in learning somehow at the beginning. So to summarize, we had now 5 different types of algorithms. First, we added the first momentum. That is like this direction here, which we added, that you're going faster in the same direction. Then we added the second momentum. First, removed the one again. There was this one that we are doing differently on different directions. And then we combined all these things together, and then we ended up with our Adam algorithm. Good. So do you have any questions to that? Good. Then, yeah, to summarize, what you should hopefully remember is the general training algorithm, then how to like do the feedback, and then the main 3 things when you do gradient descent, how to do the stopping, how to select your sample size, and then what type of update rule you are. Again, since it's like you might go too fast or too small, you have to use the right type of heuristic on which information to consider there. There's no more questions, then we'll have an exercise on next Tuesday, and on next Thursday, you have all day off, and then we'll see you again the Tuesday afterwards.